Assalamu alaikum, everyone. I hope you are having a great weekend. It's me, Bouhsine. I'm a machine researcher and an AI Google developer expert, uh, currently based in the San Francisco, California. Thank you very much, Devmina and Leila, for hosting me. I appreciate all the efforts and things you are doing for the region. Thank you very much for having me. Today we will be looking at one of the actually just topics that really kind of caught my attention for the in the past few months, which was kind of really promising when the paper came out, and it was really interesting to see how we are actually just kind of going back to some of the I would say some of the insights that were found during the recurrent neural networks era, and we started reapplying them to actually make the transformers more stable and more efficient without actually increasing the cost, and while decreasing the inference cost by using multi-token prediction. If you checked, or if you were kind of following the recent events in the world, about the the recent actually just findings of on recent models that are coming out from the big kind of companies, and also the big open source communities and stuff like that, you might have just kind of blown out by the performance that DeepSeek kind of provided, and how it shook the whole Silicon Valley in the past few weeks. And one of the things that they just release, instead of just kind of instead of using Mixed Express to actually create a large model, and also the different other RL training schemes, and also the how they were able to create and optimize their kind of software and their CUDA code to actually just work on smaller models, and to work on smaller, or to make training itself cheaper and more stable, especially at large scale. One of the other things that they also did was to use the multi-token prediction, which is kind of an interesting idea, that kind of states instead of in causal learning, as we saw last time, you are basically kind of limiting your model to only predict the next word, or each word to just predict the probability of the next word appearing, which is a bit kind of limiting, not limiting, but it kind of does not provide you with enough information about what are the next three tokens, for example, especially if you are using a tokenizer that splits the word into multiple tokens instead of one token. For example, if you are using byte pair encoding, you are basically just for each word, when you pass your words to the encoder, you are basically not just kind of getting an ID for this word, but it will be combined to create multiple smaller tokens that allows you to actually predict the next token, or just to have an ID for that word, or multiple IDs for that word. So the word itself will be chunked, and then you will create for each chunk, you will have an ID. So a word might have either one ID or multiple IDs. Similar, let me just show you an example here. Similar to this, for example. So you have this, it will still stay this, but is will not stay as not. It will just be split into multiple tokens to actually present to represent this token specifically. So when you are doing like next token prediction, basically you lose the ability to actually know the whole context of the phrase, and especially you lose the ability to know what are all the tokens that kind that creates this word specifically. So in a way, multi-token prediction allows this word, for example, to also be able to predict the next three tokens. So you can actually, doing backpropagation, you know that these two words always appear together. So you need to actually create a link between them in the embedding space, so you can actually create more stable like large language models. And the key idea here, is to attach like a recurrence or like a causal element or a recurrence head that after the last layer like of prediction, you will generate for each token that you have in your mask here. Like for example, in this token here, from each of these embeddings, you will generate three other embeddings, and then calculate and then do like the output layer for each one of them to actually predict the next word. And this way, it will allow you to actually generate for each one of these like three more tokens. So you will have the output of this head here, it will have three words, and then the output of this head here, it will have other three words, and so on and so forth until the last like kind of word that will predict the next four words, for example. And then during back propagation, you are passing the gradient to all those like kind of heads. So you will take each one of these words and then like kind of combine them to actually pass them to calculate the loss on them, and then do the backward on those like losses specifically. And then you can actually just like apply the gradients and just like um, do backpropagation using any optimizer. And this also like allows you like, so for example, like after the pre-training, you want to use like or you want to deploy this model. So instead of like only limiting yourself to actually generate one word at a time during the inference, you can actually start generating four words at a time. It's like you will pass it hi, hello, I am, and then it will generate four words, and then you can actually just like concatenate them with the previous input, and then generate the next four words, and until you reach the end of the sentence. You can see like how can this make your actually inference cheaper, since like you are not limiting yourself to only like predicting one word at a time, but now you can actually predict k words at a time. um, Most of the kinda the k or the number of words to predict, like most the thing that most people use is just like kind of predicting forward, since it's kind of like more stable, and it does not, I'll say like it does not introduce any like long-term information that is like will just like kind of create noise in the distribution. So basically, well, by limiting it to just like a smaller k, you gain both like the ability to actually make things faster, and also like more and faster. We will see like an example like of how you can actually just like create both a simple like model, and also like create a model with causal LM, or just like like kind of recurrence prediction that combines both the output from the previous layer, so you can actually predict the next token more accurately. We will be using Jax and Flax for this workshop, and we will try to go through the different applications, or the different like kind of just like a simple implementation of MinGPT, the same thing that we did last time. Just like it will kind of require us to just like pre-train it. So first, let's go to Kaggle again, and let's create like just a simple notebook. We will use it to actually just like get the compute and also like kind of organize our like we will be training on TPUs, on cloud TPUs. And we will require actually just like some secrets. We will first like need the HF token and also the API key and also like the entity. For the HF token, I think as we saw last time, you can actually just like get it from your accounts. You can just like kind of sign in and then just like go to tokens and just like get it. Not sure why I'm not signing here, but basically you just like need to sign in and just like you can get it, and then you can add that to the list of tokens by clicking on the add here, and then you can activate them. We will also need weights and biases, and then you can actually also like get the an API key and then just like use it for your own. You can just like copy it and then you can just like paste it in this value here and then just like name it wait and be like API key, and then we will be we will run. I will go to the Jupyter server and then we will uh kind of paste this one or just like take this URL. Let's just check it. Yes, it is the URL that we need. And we will go here and then we will go to Jupyter servers to actually just add the server URL, Kaggle, and then we'll just like parse URL and this is a proxy. So let's just get the other one. And then we will add the server. So now we are connected to the Jupyter server, and now we can actually just like code out live here. So first thing first, we will create like a new code block, and then we will just like add like just like add these following kind of scripts to actually get the secrets that we just like added in Kaggle and add them as like OS environment like to our like environments file so we can actually just like use them later. So let's just like run this. All right, and then let's just do this and then let's like just do another code and it just kind of install some of the few libraries. So we'll be reusing some of the codes that we created last time, and then we will be editing them to actually fit our own need. I'm not sure why it's not. Maybe the first one is still working. And then now we will do something. We'll create a bit of some imports just like to kind of. Okay, let's just like do it like directly in Kaggle instead. So let's just like import some of the codes. And then let's do this. Let's just like install. Okay, cool, 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 cool. And like, let's now do something else. Like, let's try to create like a mesh. We explained the mesh like last time. We will be using like a TPU V8, which has like eight devices, or like just like four, and then just like kinda two for each. And if you are like kinda creating or working on like a multiple GPU system, then you will need to do this one, which is kind of like it will calculate the number of GPUs, and then it will create a mesh of eight one. So like when you are trying to distribute your training, you are like distributing the models using like kind of all the GPUs instead of just like using one. We will be using this time. We will be using a different tokenizer. Last time we've seen like how to use like Hugging Face tokenizer. But today we will be using the tick token, since like it's a bit kind of faster, I would say, TPU, or faster like tokenizer that help us um, transform like or it will help us actually just like transform um, the whole the whole system using actually just like kind of use what's happening here, mesh shape. Okay, cool, cool. So like, okay, I think it's done. Yeah. We will be copying again the same um, like transformer block that we created last time. This is basically just like a causal LM that create the causal mask we talked about here, this one, and then followed by like a transformer block. You have your usual multi-head attention, and also like your linear, your first like kind of projection, second projection, and also just like the layer normalization, and it follows like just like a standard uh like transformer model. You have the MHA, and then you are following it by a layer normalization and then a linear, and then you are doing like another linear here. You are just like doing like a skip connection here, and then another skip connection here, just like the standard like kind of transformer block. And then you have like your own GPT model. This is where things will get a bit interesting. Um, you have like your own like positional embedding. We will see like in the next episode, like we will see the different types of embeddings, or the different types of kind of positional embedding, and also like the rotary embedding that is used by Llama and some of the modern architectures. And we'll talk about like kind of like how you can actually use it for your own pre-training, like from scratch. For the mini GPT, it's just like the standard model that we talked about like last time. Just like kind of 12 blocks, and also like with an output layer that kind of take us back to the ID of the word. And that's like kind of like just look when we call it, we are just like kind of creating or trying to get this output after passing through all the transformer blocks. And let's just like kind of run it. And for the data set this time, we will be using directly like just like Hugging Face. So we will need to change a bit. Like last time we used um, a transformer, I would say, like a kind of a transformer block, not a transformer block, but we used what do you call it, like kind of a text file, and then we loaded the data from that text file to actually do the training. And today we will be changing that a bit, and just like kind of uh, getting more like streamed data directly from Hugging Face instead. And this is like our loss function. The only change like that we did from the previous loss function is like let's just go check the previous loss function. Uh, the previous like time that we did this, we just like created like kind of a mask, and then we used that mask during our train phase. Where is it? Yeah, this is the loss function. So basically, we just like took the prediction, and then we just like predicted the next token, or just like try to create like we just like shifted the words of the in each sentence just like by one, and then we used like the logits that we got from the model directly to compare it with the logits or the labels that we have. But this time we will not be doing it like this. So like we will be doing a bit of kind of like manipulation inside. And if we are not, like for example, this is like kind of the standard way when you have a k is equal to 1. So this is equal to whatever we did in the past time. And but for this time, we will be changing that a bit. So basically, we need to first calculate what is the new sequence length, or like how big our kind of should our kind of like input like phrase be. We need to kind of reduce it by the number of next token we want to predict, since like it will create, if we did not do this, it will create a conflict at the end when we reach, for example, the end of the last word of the phrase, and we want to predict the next word. We don't have in like any four words, like since we already like kind of use all our words, so we will need to keep kind of like four words from the end, and then just like kind of keep them as a reserve, so we can just like use them for our loss prediction. And then we will take the inputs like, or the batch input, and then we will just like go from the first like word until like we reach like the last four, or just like we stop before the last four. And we can actually just like use this phrase here for the forward projection, and we can create the logits using this input here. And then now, once we created the input, we can actually do a simple like next k projection, instead of this is without any causal LM or anything like that. This is a kind of a basic way to do it, which is just like instead of predicting from the, or instead of calculating the loss only on this token alone, you calculate it for the next k token for each of those words until the end. And then you can actually use this information. You can just like kind of slice your targets or your input. You will use like the dynamic slice from lax, and you will just like split the batch, the original input, to have like to start from like the index that you are trying to attend to. For example, this is the first prediction, until like the next four tokens, like so you can actually calculate like kind of the loss, or I would say calculate like just extract the next four tokens, for example, like just like from your input batch, and then you will calculate the softmax cross entropy on it, and you will just like pass this targets that you created to actually calculate the loss, and then you will just like create the average of that loss, and then just like you will return. Another way, another thing what we need to do is like to have a training like kind of step similar to whatever all the scripts that we have previously. You have like kind of a lambda function that will take all the keywords and do like the grad function on it, and then it will just like pass this like kind of to the model and also the batch, and then it will pass the number of tokens we want to predict next. and then we will use it to actually get the loss from this one, from this function, and then apply the gradients like using and the optimizer that we have. Similar to like what we did, just like the only change is the number of next tokens. And then there's like the eval step. And now like for the main, we will first have a config file. This config file is a bit kind of just like a simple config file that contains all the information that we have. We first like have the vocab size, of course, like we have the number of like transformer blocks. What is the max length of our forward, like of our like phrases and stuff like that. And also like just like kind of basic stuff. We will be using this one here, like the max token to process, to actually just like stop the training after 600 million tokens. And then for the eval steps, this is like kind of will be used to actually limit the evaluation steps that we need, and also like what is the frequency of our evaluation. For the for the set size, we will take like just like 10,000 like inputs from the data set, and we'll just like kind of cache them so we can actually predict like, or just like we can use them for the evaluation after each 200 steps. And then for the checkpoints, we want to save them like every 10k iterations, and we'll save them in this one, and this will be our kind of let's just call it dev. This will be our weights and biases kind of like project name. And for the number of words, let's just like do 4 for now, and we can actually just like use it for our prediction. You will need to do a bit of kind of calculations, just like to see how much like words or how much tokens per iteration. For this one, we will be just like using the batch size and also like the max length, so to know like how many tokens are we consuming per iteration. And this information will provide you with kind of a link to this one, so you know when to stop. You don't want to kind of like exceed 600 million. For example, like this will require us like 3 hours of training. And this will be used to actually calculate what is the maximum iteration, like iterations that we need to do. And yeah, and then let's just like kind of run it. How we will initialize our weights and biases kind of model. I think we already like have a, oh, we did not run the, okay, we forgot to run this one. We forgot to run, we'll just like run it for now here, and then we can just like push it. And then let's just like take it up. Okay, so we need to do a bit of trickery. Okay, cool. Now we have we already like have a run in weights and biases, and we can actually just like follow all the runs that we have. But for now, we only have one, so like it's cool. Let's do this right now. Let's just create a bit of code so you just so can actually breathe a bit. We will create our model using the create function that we had here. Where is it? Where is it? Yeah, this create function. It will allow us like to kind of use the config to create the models using the function that we defined here. And then we will actually configure the ORBAX model. to actually just like to define where should we save our models, and then we will load our data and then just like prepare it. So basically, we'll be using fine web datasets, and we will also be using the training splits. And this is the key, kind of the most powerful feature of this load dataset, which is like just streaming. So instead of like downloading all the datasets to your local machine and then like uh, training on it, you can actually just like stream it directly from Hugging Face and load the data directly from Hugging Face whenever, or download it whenever you need a batch. You will just like download it directly from Hugging Face and load it on memory instead of just like trying to load it on local machines. Sometimes like you don't have enough hard drive, for example, on Kaggle, you only have like 40 gigabits of like kind of space of this space. And when you want to train a large, well, like on a larger data set, you cannot download like 200 terabytes of data on your own machine. So basically, you would just like be streaming it directly from Hugging Face and just like using it for that. But first, like from this data set, we will be using we will be taking, as we said, like taking kind of a few examples and then keep them as like a validation set, and then we will skip them from like for the training set. We will skip them those 10K images, and then we will just like process that image using our like process function that we talked about earlier, that we talked about like last time too, which is just like kind of adding an int of text at the end and just kind of like trying to just trying to encode the information using the tokenizer. And then we will create iterators from it. And then just like to this, we can actually just like kind of pass it to our training loop, which is the same thing, which is the thing that we will be getting to next. It's still loading the data sets. Uh, while we wait for this to finish, let's kind of go through the iterator. It's like the same kind of training step that we've seen last time. And there's like there's like no difference. Like basically you will take the batch that we get from this iterator here, and then we will put it like we will shard it through across like different devices, and then we will pass it to the training step to get actually the loss of this on this one, and then like kind of we log it to weights and biases and see like how it behave. I think that, yeah, it's already done. Let's take a launch it first. And then we will just like validate it every now and then. And then we'll just like kind of use the validation loss to actually track the validation. And also like whenever we have, I think we need something. And we removed 1 hour for some from this function. Okay. So this is like one way to do it. And the other way is a bit kind of similar in a similar way. But let's just like kind of first like wait for this one to finish. And let's see the logs. Yeah, it's running. You can see like the network traffic kind of increased since we downloaded like the first batch of our datasets. Yes, like we start kind of getting the training loss from the notebook. However, like this is not the best way to do like a multi-token prediction. And the main problem of this way is like, so each token here does not rely on the previous token. In the um, in this one, like when you predict the next token or the next four tokens, like after each token you predict for one token, you actually need to rely on the results from the previous one. So you should not just like kind of keep on predicting things kind of separately. You need each token that you predict to have like a bit of information about like the previous like token, since this is like kind of like you are not doing like you're not doing like just like kind of the probable, or you're not predicting only one token based on the previous token, but you are predicting like kind of k tokens based on the previous token, and then from each tokens from these tokens it needs to rely on the information of what was the token that was predicted before it. And this is the main idea that was kind of like implemented also in DeepSeek. It's not only just like GRPO, but also like this was also like kind of used to actually give them or like help the model reach its own like kind of yeah, this was like the paragraph where they will talked about it, that helped the model kind of reach this results. And let's see the training script, and then we can stop it if we already got. And you can see like the training is already like decreasing, and it will keep on like kind of improving until the end. But now let's just like check something else. Like we will be doing a bit of change. So instead of having a GPT that relies only on one prediction, we will change the implementation to include a causal head, which will just like include one dense layer that will predict the next token, and then one output layer that will kind of create the output for that specific word. And we will use this causal head to actually create multiple heads for prediction, and it will allow us to create that kind of reliance, or like just like link between the different K tokens that we have. And let's see. So like you can see like how it's still progressing, and it will keep decreasing until it reach like 2.8 and stuff or something like that. So let's just like stop the training and let's just like try this new one. And then we can actually create an updated function here, which is the loss function. So here, instead of having like the previous one, instead of having kind of a prediction and then just like taking the model prediction and just like kind of splitting it, what will we be doing is like we'll be splitting both the logits and also like the like we'll take the list of logits that we get from the model, since the model is not only like kind of giving us like one token for each of like the causal mask, but we will be predicting the next K token using it. So we would append kind of the outputs from each head that we had from the causal LM, and it will give us like a logit, and then we will save it to this list. And then we will be using this list specifically to actually calculate the loss function across the different targets that we have. We will be still using dynamic slice on the targets from the batch to actually extract the k to k the k, I would say, the keywords. And for each like head prediction head from the logits, we will be calculating the loss separately, and then we will be summing it and just calculating the average on it. Everything will still stay the same in the training loop. Nothing will change. Let's pray to God that this will work. I think we need to recreate the model. Plus, we need to take the function, the create function. What was the name of the K in the config file? Yeah, it was like also called the prediction horizon. And we will be using it to actually create our new model. I forgot a comma here. Okay, and then we will just continue. And then we forgot something first, like we need to separate between the different kind of dot finish. Come on, cancel one. Okay, let's just like finish the previous like run, and then we can actually just like init another one. And when you go back to the weights and biases, you can see like that you can actually compare between the different runs. This was like the previous model that used like just the basic loss function or the basic kind of architecture. And this new one, the pink one, is the one that is using the causal head. Hopefully we'll receive our first. Yes, like so we received the first loss function or loss value of the first iteration. And now you can compare both of them, like how they actually optimize. And let's see if this kind of like helps in a way for just like from a loss function. You can see like that how the loss function now is really kind of decreasing faster compared to the previous one, when we did not use the causal LM head. So this was like kind of small, I would say. Just like do a quick start, quick save, and then just like call it dev mena for dev mena. And let me share with you the link if you want to access it or anything in the future. And let me send that StreamYard. If you have any question, feel free to ask. If not, if you have any questions, feel free to ask. Uh, if not, thank you very much for having me here. I hope like you learned something new, and hope you enjoyed it. Thank you very much. Appreciate it. Thank you, Leila.